السلام عليكم. So today we have another technique of spectroscopy. It is infrared spectroscopic. Or called IR spectroscopy. And it is more complicated than UV visible spectroscopy. An infrared spectroscopy, which needs longer wavelength than UV visible, and it's the measurement of the interaction of infrared radiation with matter by absorption, emission, or reflection. It's used to study and identify chemical substances or functional groups in solid, liquid, or gaseous forms. Infrared region comes after visible region and before microwave region. And as I mentioned, it is longer wavelength of UV visible region, I mean. And IR refers to the region of spectroscopy between UV visible and microwave region, and it can be divided to 3 main regions or 4 regions. So the main regions are near IR region, and this region of the electromagnetic spectrum from 800 nanometer to 2500 nanometer, or 0.8 to 2.5 micrometer. And this region, or this technique, mainly used or typically used in application including medical and physiological diagnostic research, including blood sugar, functional neuroimaging. Another region is mid-IR, and this region from 2500 nanometer to 5000 nanometer. It includes vibration, rotation region. طلاب رجاء ان المايكات مالتكم ولا زحمه. طلاب مايكاتكم لان صوت اطفال. Third region is far IR, which called rotational region, and this from 5000 nanometer to 10,000 nanometer, or 100,000 nanometer. The most important one, which from 2.5 to 25 micrometer, which is called, it's nearly from mid-IR region. It's from 400 to 4,000 centimeter -1. So we'll deal with wavelength in IR spectrophotometer. Here we have a chart or spectrum to benzoic acid. It is an organic molecule, contains functional group, hydroxyl and carbonyl group. So hydroxyl can be seen around 3,000 centimeter wavelength, and carbonyl can be seen in about 1,700 centimeter. Another example is the ethanol, and it is organic solvent. Ethanol has only hydroxyl group, and normally hydroxyl group can be seen around 3,000 centimeter of wavelength. Ethanol hasn't another functional group except the hydroxyl, which appears in this area. It has CH3 and CH2, and those bonds can be seen in fingerprint area here, down 1,000 centimeter. So what is the principle, or what are the principles for IR spectroscopy? As in the UV visible, in the UV visible, the transitions from lower to higher level of energy can cause the UV spectrum. In the IR, similarly to the UV visible spectroscopy, when IR light is passed through a sample of organic compounds, some of this light frequencies will absorb while other will be transmitted. يعني مثل ما شرحنا بالUV visible spectroscope في مطيافية الأشعة البنفسجية الفوق المرئية، أو العفو الفوق البنفسجية المرئية، إنه إذا سقط شعاع يناسب مستويات الطاقة الموجودة بالجزيئة، راح يثير الإلكترونات من مستويات الطاقة الواطئة إلى مستويات الطاقة العالية، ونتيجة هذه الإثارة تظهر على شكل طيف. وممكن قياس هذا الطيف إما بالامتصاص، يعني الانتقال من مستويات طاقة واطئة إلى عالية، أو بالانبعاث emission. الإيميشن يكون من مستوى بالعكس، من مستوى طاقة عالي إلى مستوى طاقة واطئ. مطيافية الانفراريد الحالة مشابهة، لازم الشعاع الساقط يناسب مستويات الطاقة اللي هي Rotational and Vibrational levels حتى تتمكن المادة من إظهار طيف الأشعة فوق فوق الحمراء، العفو، من ظهور الشعاع الانفراريد. So we get IR spectrum by plot of absorbance or transmittance versus wave number, but usually, conventionally, we use transmittance. يعني إحنا ممكن نلاحظ بعض الأطياف عبارة عن علاقة بيانية بين الويف نمبر مع الترانسميتنس أو الامتصاصية، لكن المعتاد عليه usually نستخدم الترانسميتنس. Because the numbers are more manageable. Why we use wave numbers here? Because it is or are more manageable than wavelength as in the UV visible. بالUV visible إذا تذكرون كانت العلاقة البيانية بين الابزوربنس والطول الموجي. بالاي ار ما راح نستخدم الطول الموجي، يعني راح تكون عندنا الاعداد كلش كبيرة، راح نستخدم العدد الموجي هنا. فالعلاقة البيانية عبارة عن امتصاصية مع عدد موجي أو نفاذية transmittance مع العدد الموجي. The principle of linked to the vibrational and rotational energy of the molecule. We can see the IR spectrum when the frequency of the IR radiation is equal to the natural frequency of vibrational to the molecule. يعني لما يتناسبون proportional راح يحصل الامتصاص، وبالتالي give us the spectrum. And as in UV visible, the absorption of IR radiation causes an excitation of molecule from a lower to the higher vibration levels. The important thing to know is each vibrational level is associated with a number of closely placed rotational level. يعني كل مستوى اهتزازي مرتبط بعدد من مستويات طاقة الدوران اللي تكون جدا متقاربة. For this reason, IR spectroscopy, sometimes called vibrational rotational spectroscopy, because it depends on those movements in molecules. And not all bonds in the molecule are able to absorb IR energy. مو كل الأواصر الموجودة بالجزيئة قادرة على امتصاص طاقة الانفراريد. فقط الفانكشنال جروب، فقط الفانكشنال جروب، المجاميع الفعالة الموجودة بالمركبات. ولهذا نشوف الاي ار مو دائما فعال، not always active, not always useful. So it is are able to absorb IR energy, but only those bonds which are combined by a change in the dipole moment. يعني الجزيئات اللي بيها dipole moment، عزم قطب. على سبيل المثال الهوموجينيوس gases N2 O2 هذه ما تنطينا IR، يعني ما بيها عزم، ما بيها عزم قطب، القطبين متشابهات يكونون. لكن الجزيئات اللي بيها dipole moment ممكن إنه تظهر أو تستجيب للإنفراريد spectrum. So the transition which are not combined by a change in the dipole moment of the molecule are not directly absorbed. Not directly absorbed and are considered as IR inactive. The changes in the vibrational energy depends on 3 factors. First one, mass of the atoms present in a molecule. Second one, strength of the bonds. And arrangement of atoms within the molecule. So no two compounds can be or can have the similar IR. There are no two compounds similar in the IR except the enantiomers, if you remember this term. Enantiomers, stereoisomers that are as a mirror image. So those two isomers, they are similar in the molecular weight and in the functional group here. So they have bromide, chloride, CH3, and hydrogen. But in the IR, they different in the mirror, as you see here, but in the IR, they are similar. Why? Because they have same functional group, so we can't distinguish between them in the IR. So they are, with these compounds, is inactive. So let's see the requirements of the IR technique. When we need to do the IR, we need to correct wavelength, as we mentioned or discussed in the UV visible spectroscopy technique. So we need to put blank to make the absorbance at 0. With the IR, we need to correct wavelength of radiation if a molecule absorbs radiation only when the natural frequency of the vibration of some part of the molecule is same as the frequency in incident radiation. Another thing, electric dipole, if frequency of vibration of HCl has a dipole moment exactly match with that coming from the source, means the light of the instruments. So the IR will take place, or we can notice the spectrum for the IR. With molecules such as oxygen gas, nitrogen gas, chlorine gas, no net change because they haven't dipole moment. So we can't see IR, as I mentioned before. So the IR is inactive in this case. The theoretical aspect regarding the IR spectroscopy . So what happens when the molecule absorbs a frequency less than its frequencies? Whoops. So when a molecule absorbs radiation with a frequency less than 100 centimeter minus 1, the molecular rotation takes place, and if a molecular absorbs more energetic radiation in the range of 10 exponential 4 to 10 exponential 2 centimeter minus 1, molecular vibration takes place. A single vibrational energy change is accompanied by a large number of rotational energy change. and thus the vibration spectra appears as vibrational rotation band. مثل ما ذكرت قبل شوي الاي ار اعتمادها كلها على الطاقة الدورانية أو الاهتزازات الدورانية أو الاهتزازية العفو الطاقة الاهتزازية والدورانية. So there are, or fate of absorbed radiation, there are three main processes can the molecule absorb the radiation. Each of these involve an increase of energy. So in all of those three processes, there is an increase in the energy. So first rate occurs when absorption of radiation leads to a higher rotation energy level in a rotational transition. Second rate occurs when absorption of radiation leads to higher vibrational energy. So first one in rotational, second one in vibrational energy level. In vibrational transition. So they are opposite each one other. Third one occurs when absorption of radiation leads to higher electronic energy level in its electronic transitions. So similar to the UV visible, we dealt with the electronic levels. So here are the levels. This is the energy levels diagram. So we have in the ground state rotational energy levels and vibrational energy levels. So we can see the rotational energy level, they place within the vibrational energy level. And all of those called electronic energy level. I mean, the rotational and vibrational levels, they are as a sub-levels from electronic levels. There are two criteria must be satisfied by the molecule for the absorption of IR. First one, the molecule should possess vibration and rotational frequency, as I mentioned before a few minutes. Second one, the molecule must give rise to a symmetrical charge distribution. Three main types of absorption bands occur in the IR. So what they are? Fundamental, overtune, combination. It's combinational. Let's see what mean each one of them. Fundamental, or sometimes called normal mode, of an oscillating system is a pattern of motion in which all parts of the system move at the same time with the same frequency. Combinational is the third one here. Combinational bands are observed when more than two or more fundamental vibrational are exist in the same time. These combination modes arise from the unharmony of the oscillator, which lead to interaction of the vibrational states in polyatomic molecule. Third type, which called overtone, and it is multiples or given frequencies. It results from excitation from ground state to higher energy states, and overtone occurs when a vibration or vibrational mode is exist from level V0